Hey, today I'm going to be going over with you an introduction to quantum or wave mechanics, and specifically the electronic structure of an atom. Okay, so let's go over some of the historical developments. Now, one of the first big discoveries in the nature of matter was the discovery or the proposal that all of matter is made of what we call atoms nowadays. And this was done by Dalton back in the 1800s sometime. And basically, it just said that all of matter is made up of these things called atoms. There are different types of atoms, and there's different compounds that bond together the atoms of different types in different ways, and that a reaction is simply just a rearrangement of those atoms, unsticking the glue that holds them together and then sticking them to other atoms forming different compounds. And just to show you that idea of what Dalton showed us, let's talk about methane, or specifically CH4. Now, I've color coded this such that everything inside this black box here is either color coded purple, which represents a hydrogen atom, or green, which represents a carbon atom. So each molecule within this box has one green dot and four purple dots around it. So within here we have 7 molecules of methane, each of which, if we pluck them off, if we pluck all of the hydrogens off each of the carbon, each methane molecule is made up of 4 atoms of hydrogen and 1 atom of carbon. Okay, so that was a huge discovery in the 1800s. The next obvious step really was, well, what are the atoms composed of? And what's inside that atom? And then also, what holds the atoms together, and how do we understand that? And so the secret to that lies in what's called subatomic particles. And the first two, I guess, of which were discovered by Thomson and then shortly thereafter by Rutherford, which is that atoms contain a central positively charged nucleus. And so that's where the protons were discovered in the nucleus, and the electrons surrounding it. Thomson was the one who discovered the electron, and Rutherford discovered not just that there needs to be positive ions or protons in the atom, but that they're in a centralized location in the center of the atom. And so this was the new view of the atom. So within each atom, you had a positively charged central nucleus. Surrounding that, you had electrons. But after this, scientists then wondered, well, how were the electrons then arranged around that nucleus? How would they then interact also with the electrons of other atoms? And that, I'll give you a hint, is the key to understanding bonding, or the glue that holds atoms together. So before we go on to the next development along basically how to understand how the electrons are structured within the atom, it's important to understand some of the key discoveries that were made next. And this was done by chemists, physicists alike. And that is that particles can act like waves, and waves can also act like particles. So this was termed the wave-particle duality. And in principle, this is the reality of things. There's a lot more complications. Yet a bit more specific. It only really, so a particle, like something that has mass, um, you really only treat it like, or you say that it has wave-like properties when under certain circumstances. So particular for particles, when they have really, really tiny masses and they're confined in space somehow. So then we can treat them as, then they'll have properties like particles and waves. Similarly, waves, it was found, have properties obviously of waves since they're called waves, but under certain circumstances You can also treat them in some particulate ways as well. And this was really confusing to the to what physicists and chemists knew before that, which they called just the classical description. And in physics, you more or less have matter and electromagnetic radiation. So matter is just like particles, something that has mass, and waves are like the electromagnetic radiation or light. And so a particle, classically, you'd think of a particle as just something, well, something that has mass, like a baseball, for instance. And under the action of gravity, if you throw that baseball up into the air at some angle, it's going to have some trajectory. In other words, you're going to be able to pinpoint exactly where the ball is and its velocity at any given point in time along this dotted path until it hits the ground. And so the velocity and position are known at all times for a classical particle or something that has mass. And in other words, it is also localized because we know the position and the velocity to exactness at every single time. Now, a wave, on the other hand, you think of a wave as, well, a sinusoidal wave. That's the most basic model for a wave. And you might think of ocean waves at a specific snapshot in time, or if you were to allow a trampoline to vibrate, the vibrations are represented by a wave. So now to compare this with the particle, the position of the wave is not defined, and therefore the position of it is quote unquote delocalized. You might wonder, well, oh yeah, I can pick up a position along the wave and put a particle there and see what happens. Well, that's true, but the wave itself is actually extended in space. So the wave is the entire wave. So it's technically not localized to any one position. And so therefore we call it delocalized, or in other words, it's smeared over space. Position is not defined. Now that we understand a little bit about particles and waves, the classical description of them, as well as the fact that we know under certain circumstances particles can also behave as waves and waves can behave as particles. The first one of which is going to be more important when we go on to the next section. So now getting back to our sort of timeline of understanding electronics or understanding this subatomic structure of atoms, the next big discovery was the experimental determination of what's called the atomic hydrogen spectrum. And so what they did was they hooked up a high voltage source to basically a chamber filled with molecular hydrogen, so H2 gas inside of there. And this high voltage, they allowed basically a huge arc or like a lightning bolt to shoot through that gas, which essentially just provided it a ridiculous amount of energy in order to split the hydrogen molecule into its component atoms and also leave the atom in a highly excited state, which just is another way of saying it's a high energy hydrogen atom. Now, what happened was in this experiment, and they were really just looking for how the electrons were well, what the different energy levels or energy distribution of the electrons were in an individual hydrogen atom. So they measured actually the emission spectrum of what happened after we had an excited hydrogen atom with high energy. And the results were quite striking in the following sense. They measured the electromagnetic spectrum, but only along in the visible spectrum. So I have a blue line, which is 434 nanometers. That's just a wavelength that associated with a specific energy of that light. There was green, a line at green at 486 nanometers, and also at red, which is 656 nanometers, also having a different energy. And the interesting thing about the atomic emission spectrum of hydrogen was that only specific energies were observed. Only specific energies. So what that implied in the atom was that electrons, they could only be in particular energy levels and nothing in between. So the blue energy line, or that was observed, is represented by this blue squiggly line over here. So between a high energy, so the electron relaxed from a high energy state down to what looks like the second level. The green was something that was slight, let's say that the fourth one up down to the second one, and then the red one was the electron relaxed from the third level to the second level. Okay, so the key point here is that the electron energy levels, they observed, or they interpreted the data such that the energy levels were quantized, which is to say that only certain energy levels were allowed. Okay, so now in order to explain this, Niels Bohr, who was a student, I believe, of Rutherford, he came up with a model to try to explain these results from the atomic hydrogen spectrum. And he came up with a model for the hydrogen atom, and specifically how to understand the energy levels of the electron in terms of physics of particle dynamics, and particularly how the electron moves around the nucleus under the influence of the Coulomb force, which is the force that holds negative and positive charge together. And so the important aspects of this model that he developed was that he treated the electron, which we know has mass, very tiny mass, but has mass. He treated it as a particle. So the way he treated the electron itself was classical-like. However, however, the way that he matched this up and fit the behavior of this electron in the various energy levels was that he said, well, I don't know why it needs to be true, but I know that I'll assume that the angular momentum of the electron at variety of distances or orbits is going to be quantized. So he just assumed that should be true, even though he didn't really know why. So basically, he just fit this data, and it happened to work. So the way he treated this, or well, the outcome was that the electron could only be at particular radii of orbits away from the nucleus. So, and we have n is equal to 1 is the closest one, then 2, then 3, then 4, then 5, etc. as we move outward. Now, the position and the velocity of the electron in any of these given states, the n is equal to 1, 2, 3, 4, or 5, it's known exactly at every point in time. So that's why the electron is a classical particle in this description. The energy, however, because of his assumption that the angular momentum should be quantized, that means the energy should be quantized also, which is just to say that the energy diagram for this model matches up with the atomic emission spectrum for hydrogen. So the energy is a function of n. N is just an integer going from 1, 2, 3, 4 all the way up to infinity, and the energy changes according to the n value. So this was really great because it captured the quantized nature of the electron energy levels that were interpreted from the atomic emission spectrum, and actually it matched pretty dead on. It was fit, of course, but the big problem was that with this was that it only worked for the hydrogen atom, or any atom that only had one electron. If you added a second electron to this model, it did not work. So researchers went back to the drawing board. They said, well, we kind of have an idea of how these things are quantized, but there's something wrong with the treatment that Bohr used, or Bohr assumed, that's not really capturing the reality here. So 3 researchers, de Broglie, Heisenberg, and Schrödinger, came together. This was about 1925 or so, and they thought very deeply about what the Bohr model and the atomic emission spectrum of hydrogen, and also of other atoms and things like that, and also this wave particle duality, which has been a lot of research has been going on in this time. De Broglie actually, within that wave particle duality research, he actually came up with an equation which actually allows you to to determine the wavelength or the wave property of a particle using what's called the de Broglie wavelength, which is here. And that is to say the wavelength, and then they applied this to the electron because they're asking, well, if Bohr treated the electron as a particle and that didn't quite work, well, what happens if we consider the electron instead as a wave? And so what they did was they said, well, what's the wavelength of an electron? Well, the equation, this is just the de Broglie equation, which is that the wavelength is equal to h, which is Planck's constant, just some number, divided by the momentum that that electron would have if it were in a classical-like orbit. So mass, which we know, times the velocity of that electron that it would have if it were in that particular orbit. And so if you do that calculation for a, let's say, I don't know, the n is equal to 1 level from the Bohr type model, you're going to get something, and this isn't exact, but you're going to get something on the order of the size of an atom, 1 angstrom, which is 10 to the minus 10 meters. And so what that means is that the electron we should actually consider the wave-like properties of the electron, since the de Broglie wavelength in that particular scenario is on the order of the length scale of the atom, which we're considering. So that it just means that the wave-like properties of the electron should probably be important. So because of that, they said, well, let's instead treat the electron as a wave and see what happens there. Now, in this whole last part, I'm not going to go into any of the mathematics, really. There's a lot of deep quantum mechanics, and Schrodinger came up with all the math, quote-unquote, formalisms to describe all the equations and do this. That's not important. What I want to go over is just the generic thing, how they treated this. This model is called the wave mechanical model. It's called the wave mechanical model because they treated, well, the electron as a wave, and mechanical because, well, you're looking at the mechanics of this. Now, the electron, since it was treated as a wave, they thought of it this way. At a specific, Bohr type orbit, which is represented by the green circle with n is equal to 1, since we're treating the electron actually as a wave instead, and more particularly as a standing wave, which means that it's not going to change positions with time. The constraint here is that as you go around this green circle, you have to have integer numbers of half wavelengths of the wave that represents the electron. Now, it may be a little bit better to talk about this over here. If you confine an electron to a certain total length at which the endpoints are pinned, this would be like saying, let's go around the entire circle once, then you have different only specific choices of the way that the wave can vibrate, or the number of wavelengths you can have over that length. So you can have a half wavelength, you can have a full wavelength, you can have 1.5 wavelengths, you can have 2 wavelengths. So only integer multiples of half wavelengths are allowed. Otherwise, you get what's called destructive interference. They won't add up, and over time it will average out, and there won't be a wave there. If you try to add, 1.25 wavelengths along the entire circle of the orbit, it just won't. It's destructive interference. So the electron is treated as a wave, which the other name for this model in this area of science is called quantum mechanical description. Wave mechanics, quantum mechanics is really this one and the same. Now, the difference here is that the results are not orbits. We don't treat these as perfect, planetary motions where we know the position and velocity at every given time. Instead, what we get is called orbitals. That's just the name that they called these things. And the difference is that the position and velocity is not known for the electron at any given time. We basically just know a smearing of the probability of where it could be within the atom. And here up top I'm showing an example of the 2s orbital of hydrogen. So that's the second available energy level that an electron could occupy within the hydrogen atom. And so you can see that most of the probability, or most of the, little tick marks, which are basically just time-lapsed positions of where the electron could be, is mostly centered around this sort of ring around the nucleus out here. And there's a little bit closer, but most of it's out here. So most of the probability is out here. So the position and velocity of the electron in each orbital cannot actually be known exactly. We can only find the probability, or in other words, it's smeared out over space, which we expect for waves because waves are delocalized, as we've said over here. So that sort of makes sense. And the energy itself is quantized. And it's quantized for the same reason that you can only have integer multiples of half wavelengths of the wave, because only certain electron wave energies are acceptable when the nuclear potential confines it. It just means that the electron is attracted to the nucleus even though it's considered a wave. So you can only choose particular distances away from the nucleus such that you get integer multiples of the wavelength around that particular circle. So the energy is going to be quantized. We cannot have just any continuous or random energy. We have to choose. We will have only particular energy levels. And for the hydrogen atom, the energy, if you were to solve the Schrodinger equation, which we're not even going into, you're going to get out an energy which has dependence on these quantum numbers n, l, and m sub l. And that's going to show us how the energy is distributed and how many different energy orbitals we have at each of these n, l, and m sub l. Now for the hydrogen atom, the energy only depends on the first one. The other ones are called degenerate. So only n determines the energy. And this would be a good representation of the energy distribution or the energy level diagram for a hydrogen atom. The 1s is first, so that's n is equal to 1. We have the 2s and 2p, that's the n is equal to 2. The 3s, 3p, and 3d, which represents the n is equal to 3. And these are all of the n is equal to 3 are all degenerate. They are all the energies are equal for the 3s, the 3p, and the 3d. And similarly for the n is equal to 2 and the n is equal to 1. Now when you add more electrons, like when you have helium or lithium or anything like that, the degeneracy is broken. And so the S and the P and the D all have different energies, which you might be familiar with based on what's called the Aufbau principle. So only the hydrogen atom is where only the energies depend on N, but all other atoms with multiple electrons, the energy will depend on both N and L. Okay, so a little bit about what comes out of the Schrodinger equation. The actual, I guess, result, if you will, is the wave function that comes out. So this psi, Greek letter psi, which also, has its dependence on n, l, and m sub l, similarly to the energy, that's going to have a specific value at every x, y, and z in three-dimensional space. This is called the wave function. It has no real physical meaning. It's just a mathematical thing that comes out of solving the Schrodinger equation for the hydrogen atom. But the square of the wave function, psi squared, represents essentially the probability of finding the electron in that particular orbital at that particular xyz point in space. So essentially what I'm plotting up here in the top left is psi squared for the 2s orbital, or the n is equal to 1, l is equal to 0 orbital. So all this stuff is essentially the probability. So that is what's more important than just the wave function. And the important part here is that the model, or this wave mechanics, where we treat the electron as a wave, and the Schrodinger equation, which I didn't go into detail, this model works for all atoms, no matter how many electrons, and it works for molecules, it works for anything that has multiple atoms. Of course, you need to treat it on specific waves, but this is the current state of affairs in chemistry. The electron structure is treated the electron is treated as a wave, and the output is what's called these orbitals, or electron smeared probabilities, rather than perfect orbits. and these energies are quantized. Okay, and with that, I will end my video.